right, hello. This is a section of notes about the Pythagorean theorem, which is not taken directly from our book, but this skill is included in our book. I believe that it is also taught in Math 1 and Math 2, so hopefully this feels like a bit of review for you. So the Pythagorean theorem is a theorem that says the square of the hypotenuse is equal to the sum of the squares of the legs. So I come up with this little equation, and it feels like this is something that students tend to remember. This is not something super abstract. If I take one leg and square it plus another leg and square it, I get the hypotenuse squared. Any set of three whole numbers that makes this true is called a Pythagorean triple. So what I'm going to do here is I've got 5 different examples of a Pythagorean theorem here. These first 2 are common Pythagorean triples, and we're just going to go through and find the missing side for each one. I'll go ahead and write my equation up here again. I have a squared plus b squared equals c squared, where c has to be the hypotenuse. And this only works in a right triangle. So in this right triangle, for example, A, I have a right triangle. One of the legs is 12, and 13 actually represents the hypotenuse. You could use A or B to represent this vertical leg here, or you could choose another letter. So if I use, you could use A, B, or any other variable. You could use X, Y, Z. I'm going to go ahead and I'm going to pick A. The only thing it can't be is it cannot be C, because C has to represent the hypotenuse. The hypotenuse is the side across from the right angle. And then A and B are interchangeable. So I could name the unknown A and 12B, or I could switch it. Doesn't matter. So A is what I'm looking for. We'll say that B is equal to 12. And then C is going to be my hypotenuse. All right, so to solve for A, I need to simplify everything else first. So 12 squared gives me 144. Remember that 12 squared means 12 times 12. And 13 squared is 13 times 13, which is 169. I start using my order of operations backwards to solve for A squared. So I subtract 144 from both sides. $165 minus 144 is 25. A squared is equal to 25. To get A by itself, I take the square root. So whatever I do to one side, I have to do to the other. When I take the square root of both sides, we've been practicing lately that I get a positive and a negative answer, and the square root of 25 is 5. So it's true that A is equal to negative 5 and positive 5 is a solution to this problem, but it's not true that I could have both answers for this triangle. So when I go back and put it in context for this problem, we know that the length of a triangle has to be a positive number. Therefore, the missing side length is going to be 5. 5, 12, 13 is a very common Pythagorean triple. All right. So example B. Very similar type of problem. I'm going to use a squared plus b squared equals c squared. Whenever I'm missing one of the one of the lengths of a right triangle. This time, right, I always like to hone in on my hypotenuse first and kind of get that out of the way. Across from the right angle, that's my hypotenuse. This is C. So this time my unknown is C. So then I could plug in A and B for 3 and 4, and it does not matter which way I do it. I could exchange A and B and still get the same answer. So 3 squared plus B is 4 squared is equal to C is what I'm looking for. 3 squared is 3 times 3, so that's 9. 4 squared is 4 times 4, I get 16. 9 and 16 is 25. Oh, this number looks familiar. I take the square to the left and the square to the right. C is equal to positive and negative 5. So my hypotenuse here is 5. Now this is just a coincidence that the top one is 5 and the bottom one is 5. The triangle here, this is what we call a 3, 4, 5 triangle. Right? Very common Pythagorean triple. Up here, this is a 5, 12, 13 triangle. So again, when I have 3 whole numbers that make a right triangle, that's called a Pythagorean triple. But that's, it's nice when that happens, but that's not the most common kind of triangles we have. So continuing on, the next part says, oftentimes we do not have side lengths that are whole numbers, so let's play with some radicals. We recently did a radical review, so with square roots, so hopefully that comes to mind as we get after this a little bit. For these problems, I chose to not draw the triangle so that we could have a little bit of practice on making sense of these when given A, B, and or C. So we're going to draw our own triangle. I don't really know what this looks like, so I'm just going to, it's going to be vague and it's probably going to be wrong, and that's okay. Draw a right triangle, so some triangle with a right angle. Now, according to our Pythagorean theorem, A and B must be legs. C must be the hypotenuse. Ooh, spelled that wrong. If they give me A and B, those have to be the legs. So I'm going to write 5 here and 10 here, just because this length that I drew looks longer. And I'm going to reserve the hypotenuse for the side that I'm looking for. They give me A, they give me B. That means I'm looking for C. C has to be the hypotenuse. So, doesn't matter which order I set this up in. I have leg squared plus leg squared. So 5 squared plus 10 squared, or 10 squared plus 5 squared equals C squared. 10 squared is 10 times 10, that's 100. 5 squared, 5 times 5 is 25. 100 plus 25. So C squared is equal to 125, and I take the square root of both sides. $125 is not a perfect square. So we need to go back to finding the prime factors that make 125. All right, so I do what I like calling the factor tree. What goes into 125? So 2 and 25 multiplies to 125. It might be a good idea to utilize a calculator here if your brain has a hard time with this, but it is more powerful if you can do this without a calculator. 25 breaks down to 5 times 5. So that gives me 5 times 5 times 5. And when I'm talking about square roots, 5 times 5 is 25. The square root of 25 is 5. I have a pair, I bring one out. Whatever doesn't have a pair is going to be left inside. If you told me that the answer is positive and negative 5 radical 5, that would be wrong. This is a length in a triangle, so I can only have 5 square root 5. If a assignment or a quiz ever asks you for an exact answer, they want it in radical form, as opposed to taking this and plugging it into a calculator and getting a rounded decimal. So 5 square root 5. Right. When we get on to D and E, it becomes a little bit less about practicing the Pythagorean theorem and making sure that we're practicing with a variety of different numbers. So this is going to give us more practice with our radicals here. So I need some kind of a triangle. I don't really know what it's going to look like again. Maybe switch it up, put the right angle at a different spot. Maybe not. So I'm given A and B and C is my unknown. So I'll call this A, I'll call this B, and I'm looking for C. We've recently done some review with radicals, so I would encourage you to pause this video at this point and do a check for understanding. How well are you at multiplying these radicals? How did it work out for you? So go ahead and give this a pause and give this problem a try. Okay, when you start working out this problem, hopefully you notice that you have this number 3 radical 2 and you have to square the whole thing. When I'm squaring 3 radical 2, all right, you can think of that in a couple of different ways. So I can think about taking 3 radical 2 and multiplying that by 3 radical 2. So 3 times 3 gives me 9. The square root of 2 times the square root of 2 gives me the square root of 4. And the square root of 4 is 2. So I get 18 for my answer. This is the suggested way to do it. You could also think of this as distributing the square. And this works also, right? This will give you the same answer. You still get 18. Right. So 3 is square root of 2 all squared gives me 18. 6 squared gives me 36. 36 and 18, if you can't do that in your head, do it on scratch piece of paper. 8 and 6 gives me 14. 1, 3, and 1 gives me 5. Square root and square root. $54 is not a perfect square, so I'll have to do the factor tree again. 2 goes into 54 27 times. 27 breaks down to 3 times 3 times 3. So I have 3 times 3 times 3 times 2. A pair of 3s, so that can come out. And then 3 times 2 on the inside is a 6. So my value for my hypotenuse is going to be 3 square root 6. Now I want to reiterate, I know that you've done Pythagorean theorem in the past, so that skill should be a refresher. Since we recently kind of honed in on our skills on how to treat these square roots, so when I'm multiplying and dividing and squaring, kind of combining those two skills here in this activity, this set of notes. So we're going to do one more. I don't know what this triangle looks like. I like to draw my triangles different ways so that I can get used to seeing them in different ways. It's really easy to draw them the same every time and then maybe not expose yourself to other things. So I have 2 square root 3 and I have the square root, oh, stop. I have the square root of 17, but this is C. So I know that that must be my hypotenuse. I almost made an assumption that it was the leg. I'm given B and I'm given C, which means I'm looking for A. All right. So I have A squared plus B squared. When you have a number that has a real part and a irrational part, a rational and an irrational part, make sure you put it in parentheses. Because I need to square this entire number. It would be easy to make a mistake and not include the parentheses and only square the radical 3, and that would be wrong. So definitely make sure that you include parentheses on these, right? I did the same thing up here. A is what I'm looking for. So I'm going to, on my side over here, I have 2 square root 3 squared, which is the same as 2 square root of 3 times 2 square root of 3. 2 times 2 is 4, so I multiply the rational parts, and then I multiply the irrational parts. So 3 times 3 gives me the square root of 9. What is the square root of 9? 3. So when I take the quantity 2 square root 3 and I square it, I get 12. Oh, isn't that nice? Make sure you don't write another squared here. The square root of 17 squared? Well, square rooting and squaring are inverse operations, right? All right, so one undoes the other. If you'd like, you can follow our same pattern and you could write it twice. Okay, and then you could get the square root of 289, which is 17. Me, I would just recognize that squaring and square rooting are basically inverse operations, and that gives me 17. Solve for A, so I subtract 12 from both sides. And I take the square root. Square root of A squared is A. The square root of 5, if I try to do my factor tree here, there's nothing that multiplies to 5 except 1 times 5. There is no way I can simplify the square root of 5. It's already simplified. So my answer then for A is just going to be positive square root of 5. If you have a triangle length where it gives you units, make sure you include units in your answer. In these problems here, there were no units included, so I didn't need any units in my final answer. All right, thank you. I hope that you feel good and confident about this. Reach out if you need any help. Take care. Bye-bye.